Now let's look at another example. This is example 4.8. In example 4.7, we took a little bit of a shortcut and we were given the derivative of the message when we were looking for the phase modulated signal. So let's investigate this idea a little bit further, and let's think about these two questions. What if we don't know what the derivative of the message is? And what if the message itself was discontinuous? So let's consider another digital message that looks something like this, where we have a message that goes from 1 to -1, and there's very sharp changes in that message signal. So let's consider both the frequency modulation and the phase modulation of a digital signal like this one, which is going to have discontinuities, right? Because m of t jumps from 1 to -1 in no time. That means that this is going to be a discontinuous message. So for frequency modulation, let's recall that the message mt is going to directly modulate the instantaneous frequency, which means that if we want to know the angle, it's going to be a little bit harder to find since we're going to have to integrate the message. So if we find the everything for the frequency modulation, this is going to actually look pretty similar to what we saw previously for example 4.7. And so the message mt is a digital message going from 1 to -1, which means that the integral of the message is going to be some kind of triangle wave that is increasing while we have a positive number, and then it decreases while we jump down to -1 in the message. And that means that the instantaneous frequency, which is the carrier frequency plus some constant multiplied by the message, is also going to just have two values. So the instantaneous frequency is going to have only two values. And that means that the instantaneous frequency also looks kind of like a square wave. And then the angle of this is only going to have two different slopes that are possible. And so just like the phase modulated example in 4.7, this frequency modulated example where the message is a square wave is just going to have two different possible frequencies. So from 0 to 0.5, we have a higher frequency. And then from 0.5 to 1, we have a lower frequency. And if you look at the very bottom, at the phase modulated signal, this is reflected in the fact that from 0 to 0.5, we have a more bunched up signal. And then from 0.5 to 1, the frequency decreases and the signal looks like it's more spread out. So now let's consider the phase modulated case. And remember, the message mt is going to directly modulate the angle. That means that the instantaneous frequency is going to be a little bit harder to find. It's especially going to be harder to find because we know that we're going to have to take the derivative of the message. And the message has these discontinuities every 0.5 seconds where it jumps from 1 to -1. So let's see how that affects the phase modulated signal. So stop for a moment and think, what does the instantaneous frequency look like for this phase modulated signal? So think about these two questions. What does the derivative of the message look like? And what does the instantaneous frequency look like? And then also think about, does the frequency of the phase modulated signal ever change? So let's take a look and see if we can find the answers to these. So the phase modulated signal is going to be the cosine of the carrier frequency multiplied by time plus some modulating constant kp times the message. Now that message, mt, is going to be multiplied by that constant kp, which is given as pi over half. So if we substitute in the message value of 1 from 0 to 0.5, and we substitute in the carrier frequency, we can see that we're going to get a cosine of 2 pi times 10 times t plus pi halves times 1. Now you should remember that there is a identity that we can apply, and this is actually going to be equal to minus sine times 2 pi times 10. Now what happens at 0.5 to 1? Well, now the message value is -1. So if we substitute in our values for the carrier frequency in the message, we'll get a cosine of 2 pi times 10 plus pi halves times minus 1. And again, we can apply an identity and see that the phase modulated signal is actually going to be equal to sine of 2 pi times 10 times t. So from this, what we can see is the phase modulated signal is either equal to minus sine times 2 pi times 10 t or positive sine 2 pi times 10 times t. Now, the frequency is the same for both of these, 2 pi times 10. The frequency does not change whether the value of the message is positive 1 or negative 1, but the amplitude does change. So if we look at the graph of this, we can see that the phase modulated signal at the very bottom is just changing back and forth. So every time that there is a discontinuity, we can see that there is just a change in the amplitude of the signal. So at 0.5, the amplitude of this signal changes, which is the same as changing the phase by pi halves. And that leads to this case where we have a signal that goes from 0 to 0.5. And then when the phase changes, we see this case where it just flips back up and so on. So at 0.5, 1, 1.5, and so on, we have this phase that's changing by pi halves. And those changes happen when the derivative of the message, which is shown in the second graph, has these spikes in it at every 0.5 seconds. Now, the instantaneous frequency of this graph is actually going to be the same everywhere except for where those impulses are. And those impulses occur at very quickly, right? They're very, very sharp impulses that take no time, right? They occur in an infinitesimally small amount of time. So if we look at the angle theta of that cosine wave of the modulated signal, we can see that the slope is the same everywhere in that signal. So the slope from 0.5, 0 to 0.5 is the same as the slope from 0 to 1, and the slope from 1 to 1.5 is the same as the slope from 1.5 to 2. The only thing that happens is that there's a pulse in the derivative where the message has a discontinuity, and that pulse results in an instantaneous shift in phase. So if we compare these two, if we compare the frequency modulation and the phase modulation, we can see that the difference between them in an instantaneous frequency, for the frequency modulation, we have two different frequencies that occur. And for the phase modulation, we can see that the instantaneous frequency is the same throughout. And that's also reflected in the graph of the angle. For frequency modulation, there are two different slopes of the angle. And for phase modulation, there's only one slope that you can see. And the final result is that for frequency modulation, we have a frequency modulation signal that alternates between two different frequencies. First, it has a frequency of 15 hertz, then 5 hertz, then 15 hertz, then 5 hertz. So sometimes we call this frequency shift keying because each different part of the message results in a different frequency that occurs at the bottom. Whereas for the phase modulation, we can see that for each different part of the message, we have a different phase in the phase modulated signal. So because of that, we sometimes call this phase shift keying, or PSK.